All right, last week, Dr. Patrick Brown and other researchers, including myself, published a paper in Nature called Climate Warming Increases Extreme Daily Wildfire Growth Risk in California. Now, since then, there has been a fair bit of controversy around this paper, and after giving it a lot of thought, I decided that since I'm pretty new to academia, I don't think I have the knowledge or the qualifications or the experience to give a real good opinion on this matter. But I do know this paper like the back of my hand, so I thought with all the hundreds of people I've seen commenting on this paper over the last couple days, I'd imagine only a small percentage of them have actually read the paper themselves. And I know reading academic papers is pretty difficult, so I thought in this video I would just summarize the paper. And this is technically part 2. In part 1, I read the paper itself and then summarized the actual written words. In this one, I'm just going to be summarizing the figures. So I actually think this version is going to be better. I learn much more visually, so I think looking at the pictures and explaining them is a much better way to understand this paper. And the first version, where I'm just summarizing the paper, I actually recorded that before the paper was even published, and I read it a couple more times since then, so I think my understanding of the paper itself is a little better as well. So without further ado, let's find out what this paper is actually about that's been gaining so much attention over this last week. So the title is Climate Warming Increases Extreme Daily Wildfire Growth Risk in California. The main author is Dr. Patrick Brown, and then right there, my name, Holt Hanley. And just real quickly, I probably should say what my role was on this paper. So while I was repeatedly asked to give my kind of insights or my edits during the writing process, kind of have a lot going on. We had some pretty crazy weather on the Central Coast this last winter, and in my free time, I'm often making my own content for wildfire and weather in California. So I actually wasn't very involved in the writing process, but the reason I'm listed as the number 2 co-author is because the research I was doing for my master's thesis, this paper kind of sprouted out of that research, and then it ran parallel to the research I was doing, and Patrick Brown and I were constantly kind of comparing the different results we were getting because the research is very linked. In this paper, the main conclusion is that climate warming impacts wildfires differently depending on the fire. If it's really cold out and it becomes a little bit warmer because of emissions, well, you're probably still not going to have an extreme wildfire because it's still going to be pretty cool out. If it's extremely hot out and you turn up the temperature, that also doesn't really matter because, well, you're probably going to get an extreme wildfire either way. But somewhere in between those, there's that threshold where if you turn up the temperature a little bit and you dry out your fuels a little more, it can tip the scale, and then all of a sudden you have an extreme wildfire when you wouldn't have before. So that's the main conclusion of this paper, looking at how those thresholds are really the place where climate warming has the largest impact on extreme wildfire risk. And my master's thesis was examining the thresholds themselves, trying to figure out exactly where the number is for a bunch of different variables, and then actually looking at the trends in the frequency of threshold exceeding days over time. And if you're interested in that, you can check that out. But that's the link between my thesis, this paper, and why I am a co-author on this paper. So let's just go down to the first image here. And I'm going to zoom in, I think, on this top one first, because this is the beginning, this is the methods for the research itself. So there's kind of 2 problems that we saw with research in the past, trying to connect climate warming and extreme wildfire risk. One problem is the resolution of a lot of climate models is too big to look at individual fire days well. So resolution, that would be like comparing a box around the United States or a box around California to a box around San Francisco or a box around an individual fire. The resolution was just too big in those climate models. And then at the same time, a lot of the research in the past was using fire weather indices. So just an example of one is hot, dry, windy. I believe it's temperature times vapor pressure deficit, and that's your fire danger. Now, the problem with that is it's kind of humans deciding what the fire danger is going to be. Like, we're deciding what the formula is. And then it doesn't really tell you all that much to try to see how those fire indices change with climate warming, because you're sort of, I believe the phrase is begging the question. You're saying, well, fire danger is temperature times vapor pressure deficit. Let's turn up the temperature. It wouldn't exactly be a big surprise if your fire danger went up. So those are the two problems that we saw. And the way around that was using machine learning. And this figure right here is going to hopefully explain how this machine learning works. What we did was we took the fire behavior triangle. So there's three sides of this triangle that are going to impact your fire danger. You have fuel, weather, and topography. So some topography variables, you have elevation, you have aspect, you have slope. I'm actually going to get my little pointer out right here. I think this would be useful. So topography, elevation, aspect, slope. Weather, you have temperature, vapor pressure deficit, precipitation, wind. Fuels, you have vegetation, like what type of vegetation and what fraction of the land is covered in vegetation. And then dead fuel moisture. So you have all those variables. And we're looking at time from 2003 to 2020. And in this paper, we're looking at about 18,000 individual fire days. Now, 380 of those are what you'd call extreme wildfire days. It's where it burned more than 10,000 acres over a 24-hour time span. So what we're trying to do is figure out or train a model to be able to predict if you're going to have an extreme wildfire day or not an extreme wildfire day. So are you going to burn more than 10,000 acres or are you going to burn less than 10,000 acres? And the way we do this is how you train the model is you take maybe 2/3 of your data and you show it the slope, aspect, elevation, vegetation, vapor pressure deficit, temperature, all the different variables for a day, and then you show how many acres burned. If it was 500, that's not an extreme day. If it was 15,000 acres, that is an extreme day. And then if you show or it wouldn't be 18,000 for the whole training set, but if you have thousands of examples, the machine starts to learn actually exactly the same way a human does. I think that's the best way to understand machine learning is it is a lot like how a human learns. So let's say it's 50 degrees out. It rained about a week ago, so there's a lot of moisture in your fuels. It's not that windy, and it's on very flat ground. That's probably not one of those days where you'd think, oh, there's probably going to be a big fire today. Now, you know that because you felt a lot of those rainy, cold days in the past, and those weren't the days where you heard about big fires popping up. But then it might be 85 degrees, very windy conditions. Maybe you're at the peak of the California drought, and you're in maybe some slopey terrain. I think that's the right way to say it, slopey terrain. Then you might have your little alarm bells go up that probably shouldn't start a campfire today. This is very high fire danger day. You know that because in the past you felt those hot, dry, windy days, and then you've watched the news later, huge fire pops up. Or in California, you've probably even had some ash raining on your house on some days that felt like that. And over time you learn, okay, hot, dry, windy, that's big fire days. Now the advantage machine learning has is it's much more accurate, much higher resolution. So instead of just being like, oh, it was kind of warm that one day and we had a big wildfire, with machine learning it knows it was 83 degrees, your relative humidity dropped down to 9%, and your slope was 15 degrees and your winds were 35 miles per hour. So it's not just hot, dry, windy, it's the exact data points. So it's able to learn very well. And then over time, it's able to predict very well whether you're going to have an extreme wildfire day or you're not. So how you do that is you build your model so that it's able to predict. Let's see, I'm trying to zoom out here. Oh, I think I can't zoom if I have my little pointer app open. Yep, couldn't. Okay, So we take all those variables and we build this model so it is able to predict with pretty high degree of accuracy. Now, how we did this was we actually used neural networks and random forests. We had a whole suite of models, and then we took the top 10%, the best performing models, and we said we're going to use these ones. So we actually built a number of models. And then on all of your individual fires, you know what the probability is that you're going to have an extreme wildfire that day. Then what we do is we come down here, and now we're looking at this figure on the left. Notice the key difference here. You have some red squares around, so your climate models, you have altered conditions, and then that goes into your dead fuel moisture, your vapor pressure deficit, and your temperature. So what does that mean? So that means we're going to be turning the dials on temperature, vapor pressure deficit, 100-hour fuels, 1,000-hour fuels, based on different climate models. So there's the actual data that we have that matches up with the actual fires. That's our historical data. Now, you could sort of think of it as going back in time to pre-industrial times, so before any of the climate warming happened. So for that, you would turn your temperature dial down. You would maybe turn your fuel moisture up so your fuels aren't as dry because it's not as warm out. And then vapor pressure deficit, it would be, just think of it, drier conditions. Temperature goes up, moisture goes down. So I kind of messed that up there. So pre-industrial, that's going to be like there's less emissions in the air, so your temperature is going to go down and your moisture is going to go up. I got confused because I was looking at the climate models right there. Climate models, you're going to have your different emission scenarios, so low emissions, middle emission scenario, high emission scenario by the middle of the century and the end of the century. And then for that, you're going to be turning your temperature up and you're going to be turning your moisture down. So it's going to be getting hotter and drier the more emissions you have. So then what we do is we put the new temperature, vapor pressure deficit, dead fuel moisture data into a very similar model as before, but with now the dials turned, and then we calculate that risk again. And then once you have this new calculated risk with your dials turned, you can compare that to your old calculated risk, and that gives you a good idea of how much things changed because of the warmer temperatures or the drier conditions. So I think a good way to look at this is maybe this figure right here. I'll zoom way in. So it's probability of extreme daily growth. So goes from maybe 5% down here up to 25% up here. And you have your original conditions. So that's pre-industrial shown with the black. And then altered is going to be with the emissions that we had, with the climate warming that we had. That's red. So right there you can see your probability of extreme daily growth went up, and that's one individual fire day right there. And then if you look across the board, there's all these different individual fire days where it's pre-industrial in black, and then you turn up your temperature, you turn down your fuel moisture to your historical data, and then you have your altered conditions in red, higher probability of extreme wildfire. So hopefully that kind of sets the stage for what we're looking at. Now let's actually take a look at some of the results. And there's a lot going on here, so we're just going to focus on one at a time. Let's look at A first right here. So the best thing to do whenever you're looking at figures is look at your axes. Probability ratio, historical versus pre-industrial. So we're comparing what actually happened against what would have happened if there wasn't any climate warming. So with this, the whole point of this is because you often hear when there's an extreme wildfire, oh, the extreme wildfire happened because of climate change. But then you think, well, how much did it change because of climate change? This is how you find out. So probability ratio At first, this number actually confused me until I interviewed Dr. Brown, and then he was able to explain it to me pretty well. And you notice it's very different for the different fires. That's one of the key conclusions of this study. So car fire, 1.06, pretty small probability ratio. Tubbs fire, 1.49, that's pretty large. CZU, 1.24, that's pretty large as well. But right now you're probably thinking, what does probability ratio even mean? How you could think of this is your historical over your pre-industrial probability of an extreme wildfire happening. So let's use easy numbers here. Let's say you plug in all your variables into this machine learning model, and then you say predict whether it's going to be extreme wildfire, not extreme wildfire, using the historical data. So with your temperature turned up and your fuel moisture is down because of climate warming. And it says there's a 20% chance that you're going to have an extreme wildfire today. And then you say, okay, let's see what it would have been without any of the emissions. So let's turn the temperature down. Let's add a little bit more moisture back into our fuels. And it says there's a 10% risk of an extreme wildfire happening. 20% over 10%, you have a probability ratio of 2. So your ratio would be doubled. You notice a lot of these fires right there, it's not that extreme, but 1.49, that's about halfway between that. So it'd be maybe 15% above a 10%. So that's your probability ratios. The key thing to know right there is that it's different for lots of different fires. And I'll explain why that is later. Next, I think this one actually is a bit more intuitive to me. You have fraction of risk attributable to warming. So what percent of the risk of having this extreme wildfire is due to the warming that you had, is due to turning those dials? So on the car fire, for example, 6% risk is attributable to the climate warming. Pretty small. August, that was the August complex, 6%. Campfire, 6%. Makes sense because the campfire, I believe it was pretty cold out when that happened. So warm temperatures, that wasn't really one of the main factors that led to that fire being so destructive. But then you have the North Complex, 26%, that's pretty large. And then the one closest to home, at least for me, CZU Lightning Complex, 38%. So that's saying that the fraction of the risk attributable to warming on the CZU Lightning Complex was 38%. Pretty large percentage right there. Now, and maybe one thing I will say about that is when I interviewed Dr. Brown, he said this actually isn't the best number to use. I liked this more than the probability ratio just because, I don't know, for me it's a little bit more intuitive. But he was saying that sometimes that can be not actually the best number to use because there are situations where you could have 100% of the risk was due to climate warming. And that wouldn't really make sense because there's lots of different factors. So just a little side note right there. But I still kind of think that's the more intuitive of the different ways to look at this. So now let's go up to this one. Oh, and I probably should have said this earlier, but I'll put the link in the description to this paper so that you can maybe follow along with some of these figures while I'm reading it. So mid-century, end century, very high emissions, low emissions. So I should maybe zoom out there. Yeah, I think that would be a good way to show this. We're looking at the 4 boxes on the right. So let's look at the top left. You have low emissions, mid-century, and then top right, you have low emissions, end century. Then bottom left, you have very high emissions, middle of the century. Bottom right, very high emissions, end of the century. So the one with the smallest probability ratios you would expect to be low emissions, middle of the century. So we've turned our dials up on temperature, we've made our fuels a bit drier, but not that much, and only by 2050. So that is going to have an average probability ratio of 1.93. Then low emissions end of the century, that has a probability ratio of 1.96. What about the very high emissions scenario? Middle of the century, 2.5, pretty significant jump there. And then very high emissions end of the century, 5.88, so a very large jump there. Now, with that, I will point out that the very high emissions scenario here is based on, what is the exact wording? It's some kind of climate model with 8.5 in the description of it. And Dr. Brown was actually saying the turning of the dials on this is far more extreme than what's actually expected. He said that's basically like if we were to go out of our way to burn as much coal as possible. So you can almost maybe take E and F with a grain of salt, but it does, provide a good contrast to the different scenarios. And he said low emissions scenario is also maybe a bit too far in the kind of hopeful category. So you can almost take the middle of these two as what's most likely going to happen. Now, the key thing I want to point out here is that middle of the century, end of the century for low emissions is almost the exact same number. And that makes sense if you intuitively think about it, because if our emissions level off by about 2050, and we would stop turning the dials. So it makes sense that by the end of the century, it's actually going to be about the same risk of extreme wildfires as it would at the middle of the century, because we're not going to turn the dials very much more over the next 50 years. Whereas in ENF, the high emission scenario, gets to 2050, we just keep cranking those dials, and then it's also accumulating because it's also what we've done in the past as well. So that's where things get out of hand a bit. Now, again, with probability ratios, it's a little hard to think, 5.88, is that a bad number? That's where G comes in right here. I think this is a bit more intuitive. So, total number of extreme daily growth occurrences is on the bottom, and then the colors are the different climate models that we're using. So, different degrees of turning the dials. You have preindustrial, so that's going to be before warming and before drying. You have historical, so what actually happened. You have low emissions, mid-century, yellow dotted, low emissions end century, yellow, very high emissions, red dashed, and then very high emissions end of the century, red line. So now we can look at them. So observed was 380. So out of the 18,000 wildfire days that we looked at, 380 of those were extreme wildfire days. Now the black line there is what our model predicted, 362. So our model was actually able to predict correctly 362 of the 380. So that gives you a little idea of how good the model actually is at knowing when those extreme wildfire days are going to happen. So keep that 380 number, though, in mind. That's how many extreme wildfire days we actually had. So how many would we have had, theoretically, if we hadn't had any climate warming? If we had the pre-industrial climate, we would have had 289. So almost 100 less extreme wildfire days. So 100 less days where you burn 10,000 acres or more over a 24-hour span. Now, what if we were to turn the dials up with the low emissions scenario? So make it a little warmer, make it a little drier by the middle of the century. So using that 2050 low emissions climate, that 2050 low emissions atmosphere, how many extreme wildfire days would we have had between 2003 and 2020? 456. Now, what about low emissions at the end of the century? Remember, not much of a change between low emissions middle of the century, low emissions end of the century. I was actually a little confused when I first saw this because the lines are almost perfectly overlapping. So low emissions 2050, basically the same as low emissions end of the century. Now let's use the high emissions. Again, this is the one you can kind of take with a grain of salt. That's saying we would have had 524 extreme wildfire days instead of the 380 that we actually had. And then if we were to take worst case scenario possible, most likely not going to happen, but if we were to just actively burn as much coal as we possibly could, really just crank up those temperature dials, make our fuels as dry as possible, that's saying from 2003 to 2020, instead of having 380 extreme wildfire days, we would have had 786. So double the number. And again, take that one with a grain of salt. But I do think that graphic right there is pretty good at explaining what happens with the different climate models and in the different climate scenarios. So now let's take a look at these graphics right here, and I'll go over these ones fairly quickly. Let's look at the top left one first. So on the X, we have variables temperature change is propagated into. And then on the Y-axis, we have probability ratio, historical versus pre-industrial. So what this is saying, look at the very far right of this top chart. That's where you just have one variable. So temperature, 1,000-hour fuels, that's your big fuels. You have vapor pressure deficit and your 100-hour fuels. You can think of that as fuel is about the size of your wrist. It takes about 100 hours for moisture to start impacting the dryness of those fuels. What it's saying on the right here is we're only turning one of the dials. So we're only turning temperature up. We're not going to play around with fuel or vapor pressure deficit. And then we're looking at that probability ratio and how much does it change. Now, on the very far left, that's where you're turning all of your dials. So you're turning temperature up, you're turning vapor pressure deficit up, you're turning your fuels down, you're making your fuels much drier. And you can see the probability ratio goes up. So basically, in a sentence, what that's saying is the more variables you allow climate warming to propagate into, the larger impact climate warming is going to have on the risk and frequency of extreme wildfire days. Not exactly surprising. What is maybe surprising is which variables are the most important. You can see temperature is actually the least important variable, whereas 100-hour fuels is your most important variable. So what that's saying is with climate warming, how much your temperature goes up actually isn't as important as the impact that those warmer temperatures have on the dryness of your fuels. But the most important thing is that climate warming propagates into all those variables. That's where you see the biggest change. And it's the same for fraction of risk attributable to warming. Now, let's look at this one. We have 100-hour dead fuel moisture on the Y, so it's going from 0% up to 40%. And then on the X, it's vapor pressure deficit. So the reason those two variables are picked is because those two are our two most important variables, the ones that impact your probability ratios or your fraction of risk the most. The main thing to know on this one is that the bottom of the arrow is your pre-industrial climate, and the tip of the arrow is your historical climate. So the longer that arrow is, the bigger the change is because of the turning of those dials. And I think it's actually easier to look at this one on the bottom. The main thing that this is saying is that there's diminishing returns. So you see how big of a drop that is on this arrow up here. It goes from maybe 27% down to 23% fuel moisture. But then you look at these arrows kind of closer to your 5% mark. With that turning of the dial in the pre-industrial bottom of the arrow to your historical tip of the arrow, it's barely changing at all. It goes from maybe 5.1 to 5% 100-hour dead fuel moisture. What that's saying is you have a bit more bang for your buck when there's a lot more moisture in the air. So I'll use an example. let's say it's 25% fuel moisture, and you turn your dial, it drops down to 20%. But then if you're at 5% fuel moisture and you turn your dial, it drops down to 4.9%. So there's diminishing returns because it's easier to dry things out when there's moisture than when it's already really dried out. I'd say that's intuitive, but it also is fairly interesting. So now, and that is the reason that I'm going over this paper, is because there are very interesting results from this paper. And I think the most interesting results come up with this last figure that we're going to look at right here. This is the last figure, right? Yeah. Alrighty. So this is going to be breaking down the car fire on the left and the North Complex fire on the right. So I'll just show the different ones that we're going to be looking at. Daily growth is this top column, or top row. Probability of an extreme wildfire happening. Probability ratio, 100-hour dead fuel moisture, vapor pressure deficit. And you can see on the bottom, it's the dates that this fire took place. So car fire, July 23rd to August 22nd. North Complex, August 18 to October 6th. So let's just look at this first one first. So car fire, this is showing how many acres burn per day. And that little dash line is the line that you have to cross for it to become an extreme wildfire day, shown as the little pink, maybe magenta circles there. So you can see we had a couple of extreme wildfire days at the beginning, actually quite a few extreme wildfire days, but then it kind of trailed off towards the end there. And then with the North Complex, not that much going on. And then we just had a massive fire day, and then came back down again, and then 2 more extreme wildfire days. So now this next one is going to be probability of an extreme wildfire day happening. And your first question is, why are there so many lines? Well, that answer is shown at the top. Red is going to be your very high emissions end of the century. Low emissions end of the century is yellow. Black is your historical predicted. Blue is your pre-industrial. So probability of an extreme wildfire happening, and this is a time series. You can see the models show a higher probability actually when we ended up getting some of those extreme wildfire days, and then it comes down, and then it comes back up again when we had a few more of those extreme wildfire days. That shows that the model works. You have the spikes in the right times. But what's maybe more interesting is that there's different levels of risk depending on the different climate scenarios. So with your pre-industrial climate, you might be around a 0.13 probability that day, but then in your very high emissions end of century, you're maybe at a 0.16. So that's what the different lines represent. Different probabilities that that extreme wildfire is going to happen. Now let's go down to probability ratio. Now this is, actually, I'll say one last thing about probability. Comparing the car fire to the North Complex fire, you notice that the car fire actually has a pretty high probability of having an extreme wildfire day almost every single day. It's pretty high up there. And almost every day on the car fire is a higher probability of having an extreme wildfire day than the North Complex fire. That becomes important later, so remember that. I'll take a quick sip of water. All right, so here's where things get interesting. Probability ratios. So this is now comparing your pre-industrial to your historical climates. Basically, how important was climate warming for your fire danger? On the car fire, not very important at all. You can barely even see the difference in lines because they're so close to zero. On the North Complex, it comes spiking up, and then it goes down, and then it goes spiking up again. So that right there is kind of weird. There's almost no risk from climate warming on the car fire, but there's certain days on the North Complex fire where there's a lot of risk. And maybe that's the first interesting thing you can pull from this, is that it's not the same throughout the entire fire. And that's where this topic is so nuanced. is it doesn't make sense to say, oh, this wildfire happened because of climate change, because it's different from fire to fire, how much climate change actually impacted that fire. And then even on the same fire, it's different from day to day. For example, on this one, climate warming had a huge impact on the North Complex. Then around what days is this? September 8th, didn't really have that big of an impact. And then around September 22nd, climate warming, especially in that high emission scenario, big impact on your probability of an extreme wildfire. So now let's explain why. It's not just an easy generalization, and there actually is nuance. It's perfectly explained by looking at your 100-hour dead fuel moisture charts and your vapor pressure deficit charts. So we'll look at the car fire first. Here you can see that no matter your emissions scenario, whether it's pre-industrial and you have maybe a 6% fuel moisture, or it's very high emissions and you have a 3% fuel moisture, every single one of those scenarios, every single day of this fire is below the threshold that you need to have an extreme wildfire. So, just in case that didn't make sense, I'll say it a different way. 10%, that's that sweet spot where 10% fuel moisture, where that's right on the border of where you could be getting an extreme wildfire. What this is saying is that no matter what your warming was on the car fire, you had the fuel conditions necessary to have an extreme wildfire every single day. And then similar story for the vapor pressure deficit. Your threshold, I believe, was 1.5. We were way above that threshold every single day. So with the two most important variables in terms of predicting an extreme wildfire happening, we had easily met those thresholds every day on the car fire. So that's the situation where if it's already hot and dry, it doesn't really matter if you make it hotter and drier because you've already met the qualifications for an extreme wildfire no matter what. So that's why when you look at your probability ratio, climate warming, almost no impact on the car fire whatsoever, even though we have a very high probability of wildfire happening every single day. Now on the North Complex, things are different. On the North Complex, we're right around that threshold, especially around September 1st, September 2nd, and then around September 22nd through the 29th. We're right on that threshold for fuel moisture, right on the threshold as well for vapor pressure deficit, where maybe we wouldn't have had an extreme wildfire day, but then we turn up the temperature a little bit, we make our fuels a little bit drier, and then all of a sudden we are getting an extreme wildfire. So it was just that little turn of the dial that tipped the scale and made an extreme wildfire much more likely. So that's where thresholds are important. On the car fire, we're getting an extreme wildfire every day no matter what. On the North Complex, it was the increase in emissions that made the climate warmer, that made the fuels drier, that tipped the scale and led to a massive increase in the probability of a wildfire happening, or an extreme wildfire happening. And just look at those three on the far right. On the days where it's closest to the threshold, that's where we have the highest probability ratio. So that means how important climate warming was for your fire danger. When it's near the threshold, that spikes up. When it's near the threshold, it spikes up. So what this is saying, I'll zoom out so you can see all of those at the same time. What that figure is saying is that climate warming plays a role in the risk of extreme wildfires. Now, it's not blanket the same across the board. It depends on the fire. And the key thing that it depends on is how close you are to different thresholds within your variables. And in particular, 100-hour dead fuel moisture and vapor pressure deficit, because those seem to be the two most important. And what that's saying is, if it's very cold out, and you make it a little warmer, you make it a little drier, well, you're still not probably going to have an extreme wildfire. Climate warming doesn't matter for your wildfire. If it's extremely hot, extremely dry, and you make it a little warmer, make it a little drier, also doesn't matter. That's your car fire, because you're getting an extreme wildfire no matter what. Where climate warming is the most important for wildfire is when you're right on that threshold and where increasing your temperature just a little bit and decreasing your fuel moisture just a little bit can tip the scale and make that extreme wildfire day happen when it wouldn't have before. And then with the different emission scenarios, that one's pretty intuitive. The more emissions you have, the more risk you have for extreme wildfires, the higher the frequency of those extreme wildfire days. So I think that pretty much just sums up the paper right there. Hopefully you learn something throughout the course of this paper, and maybe you can understand some of the controversy that's happening maybe a little bit better. You have a little bit better background, but regardless, this paper does have some pretty interesting results, and I'm glad that you hopefully have walked away with a few of them. Thanks for watching.